All right, we're going to start talking about the quantum mechanics of the hydrogen atom and other atoms. So this is focus 8. Okay, so the structure of atoms. So we'll see first that hydrogenic atoms, so atoms are cations that only have one electron. So hydrogen, helium plus one, those are systems that you can solve exactly with quantum mechanics. Anything else is considered a many electron atom. So even helium with 2, you can't solve it exactly. And so we're going to have to start thinking about how chemists make approximations. So after we talk about the quantum mechanics for those two types of systems, we'll talk about the trends in the periodic table and atomic spectroscopy. So a lot of this is things that you've seen in Gen Chem 1 without looking at where the things like quantum numbers came from. So it should give you a deeper understanding. So I had you read a Gen Chem chapter last night, because if you remind yourself of the things that you learned in Gen Chem 1, it helps you then think about how quantum mechanics was used for those solutions. So hydrogenic atoms, hydrogen He plus, lithium plus 2, we can solve exactly and get atomic orbitals. So those are wave functions from Schrödinger's equation. And we're going to have 3 quantum numbers because we're going to work in spherical polar coordinates. So we're going to have 3 different boundary conditions. And those 3 boundary conditions will give us 3 quantum numbers, as we saw in other systems that we solved. So we can solve Schrödinger's equation exactly. This is very important. So any other atom, no, you can't. You have to make approximations. So even a 2-electron atom, and there's no molecule that can be solved exactly with Schrödinger's equation. So that really shows us that what's super important for chemists is trying to figure out how we can get approximate solutions and what sort of assumptions we can make to make those solutions as good as possible. So remember, all of this is happening at a time when we're doing new experiments. And those new experiments are teaching us new things about electrons. So at this time, about 1900, we hadn't been able to do experiments where we looked at how light interacted with atoms. And so now we could. And what was determined was when you looked at those lines in the hydrogen spectrum or any other atom, or any other hydrogenic atom, you could see that this equation could explain the lines. So this says that the frequency in units of reciprocal centimeters. So we defined this earlier, I think at the beginning of quantum mechanics. Rydberg's constant for the hydrogen atom. So this is just a constant. And shows you that those frequencies, so those transitions, are proportional to 1 over some integers squared. So N1 and N2 are both integers. And so this equation was fit to experimental data, and it was a perfect fit. So if you have a different hydrogenic atom, you'd have a different R, because Z is part of this R. So we'll see that in a second. So you could use this equation for helium plus, lithium plus 2, but you'd have a different R value. So the Bohr correspondence, or Bohr frequency condition, reminds us that the frequency of a transition is going to be proportional to how far apart the energy levels are. So a difference in 2 energy levels, delta E, in this case, if we're working in units of reciprocal centimeters, it's going to be equal to Planck's constant times the speed of light times that frequency. So this is just a general concept from spectroscopy that you've used many, many, many times in Gen Chem, Organic Chem. You would have used it in Analytical Chem. Anytime you use spectroscopy, you're using this Bohr frequency condition that says the light that interacts with your system has to have energy of its photons that's equal to the difference in energy of the transitions that are taking place. So we can explain this experimentally derived equation by solving Schrodinger's equation, so solving the quantum mechanics of the problem. So we can set it up. And the important thing here, we're not going to look so deeply at the solutions. If you take 367, you'll look deeply at the solutions and how this problem is solved. But the important thing is you have to pick a coordinate system that matches the symmetry. So if we have a hydrogen atom, you have a nucleus and an electron, and the only thing the potential energy depends on is how far apart they are, not the angle at which the electron is around the nucleus. And so that means that we're going to be able to separate the variables if we use spherical polar coordinates. So we're going to be working in theta, phi, and r. And so this potential energy that goes into Schrodinger's equation is the Coulombic potential, and it is equal to negative z. Z is the integer charge on the nucleus, E squared. E is the fundamental charge of an electron or a proton, divided by 4 times pi. I better slow down. Epsilon 0, which is the permittivity of a vacuum, and then r, the distance between the electron and the proton. So that's the potential energy that you have to put into Schrodinger's equation. You also have to put in the kinetic energy in the right coordinates, so as a function of theta, phi, and r. And so, as I said, we have 3 quantum numbers because we have 3 boundary conditions. So as r goes to infinity, then the wave function has to go to 0. You can't have it continue forever. And for both of the angles, as we saw when we solved for the spherical harmonics, you have to always repeat the same value when you go around 2 pi. So the wave function at some angle theta has to be equal to the wave function at that angle plus 2 pi, and the same thing for the other dimension, the other angle. The wave function at phi has to equal the wave function at phi plus 2 pi. So all 3 of those, each one of them will give us a quantum number, which is a result of those boundary conditions having to be met. So from quantum mechanics, you get the solutions are that the energy as a function of n is a quantum number, starts at 1, goes to infinity by integers, is equal to negative Planck's constant speed of light, Rn, so the R for the nucleus. I said that for hydrogen, it's going to be different than, for example, helium plus or lithium plus 2. Z squared, so just the integer charge on the nucleus. So hydrogen Z would be 1. Helium, it would be 2, etc., squared, and then divided by that quantum number squared. So this is the set of constants that goes into R. So it's the relative mass of the particles that are moving relative to each other. So the reduced mass in this case would be the mass of an electron times the mass of the nucleus divided by the mass of the electron plus the mass of the nucleus. So if you think about it, the electron is much, much lighter than the nucleus. So the denominator is pretty much just the mass of the nucleus. So in general, unless you're doing really careful work, the reduced mass can be replaced with the mass of the electron. So this Rydberg constant can be derived from theory to be a function of all of these fundamental constants. So mass of the electron or reduced mass, fundamental charge to the 4th, 8 times the permittivity of the vacuum squared, Planck's constant cubed, times the speed of light. And so at this time, Schrodinger was actually the one who solved this problem and came up with this energy. And it was very exciting because the RH from theory almost exactly agreed with the RH from experiment. So up here, remember, this was fit to the experimental spectrum, and they got an RH value. Down here, they used theory, and we're able to determine the RH for hydrogen. So just putting in Z equals 1. And whoops, yeah, well, just putting in the values to get Rn, and then RH is Rn times Z squared by definition. But that's very exciting that they matched almost perfectly. That said that quantum mechanics must be doing something right if it's matching the experiment. So when we look at these, we look at this equation for energy, first thing we realize is that it's quantized. It can have only certain values as a function of n, and n is an integer, starts at 1, goes by integer values, could go to infinity if we needed it to. So if we take a quick look at these energies, let's see, I'm going to stop this share and go to the figures. Yeah, go back to the beginning. So when you look at this figure, this is just reminding us of what an experimental spectrum looks like for an atomic system. And so these are the lines that were being matched when they did that experimental fit. Now, these are calculated from the solutions to Schrodinger's equation. And this shows you something about the energies. Number one, if the electron is attached to the nucleus, if it hasn't been ionized, then all of the energies are negative. It's also true that the energies are proportional to 1 over n squared. And so as n gets bigger, they get closer and closer together. Their difference gets smaller until you reach this point at which you say the energy is 0. After that, the energy would be positive, and essentially the electron would be free of the nucleus and they'd be no longer interacting. So this also, I think might as well look at this one while we're here. This reminds us that the energy of a hydrogenic atom, so a 1 electron atom or cation, is only dependent on n, only dependent on that one quantum number. So that means the 2s and the 2p orbitals are equal in energy, as well as when you get to the 3 level, 3s, 3p, and 3d are all equal in energy because of that equation showing us that their energy only depends on one quantum number. Go back to the notes. Okay, so yeah, the energies get closer together as you go up, and they're all negative because that means it's a bound state. The energy is lower than the energy would be if the electron is completely too far from the nucleus to be interacting. So when we look back at that Bohr frequency condition, back, where did we put it? Right here, we can see where that compares to theory. So if you take the equation for energy and you say, I've got N1 and N2, so I've got the energy of two different states, and I look at how far apart they are, then I just take energy of state 2 minus energy of state 1, and you come up with Hc, the Rydberg constant for hydrogen, times the 1 over the integer squared. And so that shows you that this from theory is exactly matching the functional form that was derived from fitting experimental data. Okay, so stop and do self-test 8A.1. And when you look at it, it's asking you about the bracket series. Each of the series in the hydrogen spectrum is defined in a different way. So if they say it's the bracket series, they're saying that N1 equals 4, so that you're starting your system in the 4th quantum number. And the Rydberg constant for lithium would be the Rydberg constant for hydrogen times the charge on the nucleus of lithium is 3, so times 3 squared. So those two things will help you when you work through that problem. After you work through that problem, also do problem 8A.2. Okay, so now we're going to keep talking about the quantum numbers and what information they give us. This should be something very familiar if you read the Gen Chem chapter last night. We have N, L, and M sub L. That's what comes from solving Schrodinger's equation, those 3 quantum numbers, because we have 3 boundary conditions. So the psi of an electron in a hydrogenic atom is called an atomic orbital. And when we look at it, the psi is going to be a function of 3 different quantum numbers, N, L and M sub L. And in order to solve the problem, as I said, the potential energy is only a function of R, not the angle. So we can pull Schrodinger's equation apart and we can solve the R part separate from the angular part. The angular part we already solved when we did three-dimensional rotation. So those were the spherical harmonics. So the Y, L, M sub L is the wave function for the angular component. And then you can also separate it now and get the wave function for the R dependence. So this says that capital R is the wave function. That's a function of little r, the distance of the electron to the nucleus. It's going to be a function of two quantum numbers, n and L. So n is called the principal quantum number. It has values of 1, 2, 3, etc. And what you can use it for is to get the energy. So we have an equation that allows us to get the energy as a function of n. L is the orbital angular momentum. So it gives you information on how much orbital angular momentum, so how much momentum around the angles of the atom the system has. So it starts at 0 and goes up to n minus 1. And that makes sense. It's dependent on n because angular momentum, or because energy is a function of angular momentum. And so you can't have more angular momentum than you have energy, essentially. So L is always going to be a function of n because n is total energy and L is the angular momentum. So you can use the L value to get the angular momentum. So J, which is angular momentum, is equal to L times L plus 1, all of that to the 1/2 times h bar. So that could give you the angular momentum. And then M sub L is called the magnetic quantum number. And that's because it tells you something about the orientation of the angular momentum. So it's giving you the projection of the angular momentum around the z-axis. And that allows you to think about the magnetic moment. So if a charged particle is moving, it creates a magnetic field. And so if the electron is rotating around the z-axis and going clockwise versus counterclockwise, you'll see, well, if there's just one electron going around, you'll see it will have a magnetic moment. It will be attracted to a magnet. If you put one going one way around the z-axis and equal magnitude in the other direction, going around the z-axis, so going counterclockwise, then those would cancel each other. So M sub L is called the magnetic quantum number because it's quantizing the orientation of that movement of an electron, which means you're quantizing the magnetic moment. So it has to be a function of L because once again, you can't have a larger projection of angular momentum on the z-axis than you have total angular momentum, and L gives you the total angular momentum. So it goes from 0 plus or minus 1, so which way is it rotating, all the way up to plus or minus L. And from that quantum number M sub L, you can get the z component. So you can get the projection of the angular momentum on the z-axis, which is sometimes called space quantization or orientation quantization. It can't have any orientation relative to the z-axis. Those values are quantized. So Jz, the projection of the angular momentum on the z-axis, is equal to M sub L times h bar. Let's see. So if you look at table 8a.1, you'll see the wave functions. So you'll have to trust that they can be solved. So these are the R part of the wave function. And then in the first column and then in the second column, you're given the angular part. So the R part only depends on N and L, as we show right here. The angular part depends on L and M sub L. So when you look at those two columns, you'll have to pull the pieces together. For example, if you want the total wave function, you have to multiply the first column times the second column to get, for example, the total wave function for a 1s orbital. So after you look at those, stop and do self-test 8a.3. Oops. oops, I guess that's right before it. Just reminds you of some of the things you knew from Gen Chem about the orbitals. Okay, so I've already said this, that the energy depends only on N for hydrogenic atoms. So that's because of our equation that comes from solving Schrodinger's equation that's only has one quantum number in it. And so this is just an equation. You'd think more about how this was derived if you took 367, but this is the equation that tells you the mean radius of an electron in a hydrogenic atom. And yeah, because it's hydrogenic, because you can put in a different Z. So A0 is Bohr radii, so it has a defined value. And so you notice that as N goes up, the mean radius increases. So that's something you already knew, that as you go up in N value, that means the electron on average is further away from the nucleus. For any given N and L, it decreases with Z. So if you set N and L, the average distance is going to, increase with Z. No, opposite. Because we know the larger the Z, the closer you're going to find it to the nucleus. So if N and L decrease, that's going to increase Z. So the larger the Z, the smaller the mean radius. So given N, the orbitals have about the same mean radius. So this term that your book explains kind of is insignificant because of the relative value. L's going up, N's going up. So pretty much orbitals with the same N have about the same mean distance. This term is more dominant. So some things you remember from Gen Chem 1, I hope, or from refreshing yourself, is that we have shells. Shells are sets of electrons that are all in the same N level, so have the same N quantum number. Now we're going to give those letters. So N equals 1 is called the K shell, N equals 2, the L, 3, the M, for the N. We have subshells. So all of those orbitals that have the same shape in a shell. So if L is 0, we call it S, 1 is a P, 2 is a D. So each of those would be a subshell. You'd say it's the D subshell. So the number of orbitals in a subshell, that's a result of knowing the number of Emsabel values, which oh, I guess right here we've done it completely enough to know that. So we know that if L equals 2, we have the P or the D-shaped orbitals, then M sub L can be 0, plus or minus 1, and plus or minus 2. So you're going to have 2 times L plus 1 number of orbitals. So that's what this is showing you, the number of orbitals in the subshell based on the value of L. So if it's an F, L is a 3. That means you have 0, plus or minus 1, plus or minus 2, plus or minus 3, and you end up with 7 orbitals. So stop and do self-test 8A.4, which, yeah, just reminds you of some of the properties of subshells. Okay, so the s orbitals. So we're just going to look briefly at the s, p's, and d orbitals. So this we got from the table. So I took the 2 columns and I multiplied the r for n equals 1 and L equals 0. And for the y, it would be L equals 0, M sub L equals 0. Multiplied them together. And this is a completely spherically symmetric function. A0, we have a numerical value, but it's also a function of all these constants, which you'd see if you did the total solution of Schrodinger's equation. It's often pretty common, in order to represent the shape of an orbital, is to show you the function where you have 90% probability of finding that electron. That's called a boundary surface. Let's take a quick look at figure 7. So this. So the boundary surface of an S electron just shows you that it's symmetric, spherically symmetric around the nucleus. You could draw other ones, and in your Mathematica lab, you'll create some of these boundary surfaces. Okay, so stop and do self-test A.5, which helps you think about how you're going to use that wave function. So in that one, you're talking about finding the electron in a specific location, not at a specific radius. So if you're talking about finding it at a radius, you need to expand a little bit. So r squared, the radial function squared, gives you the probability of finding the electron at a radius, but not until you multiply by essentially how many total points. So the surface area of that sphere at that radius. So the r squared part of this term comes from knowing that it's not just a single point at that radius. You want to know, for example, what's the probability of finding it at 2 angstroms from the nucleus, something like that. You have to multiply by the whole surface area at 2 angstroms. So stop and do self-test 8A.6, which asks you to do it in an approximate way. We'll redo this one in class exactly because using Mathematica, there's really not many reasons to do approximations. And in this particular one, it's asking you to make the approximation that the R function, the R part of the wave function stays constant over the volume that you're looking at. And that's hard for you to predict at this point. So I would say do 8A.6 so you know what I'm talking about. Then in class, we'll redo it exactly. Skip the justification 8A.1. Figure 9, let's look at this concept of a node, which you also learned about in Gen Chem. Yeah, so when you look at this, this is showing you the radial functions for different orbitals. So 1s, it never passes below 0. And then, let's see, 2s goes below 0 and then back and stays below, yeah, it goes below 0 and stays below 0. So that means there's a point at which it passed through 0. That point, if you squared that to get the probability, would be the point at which there's 0 probability of finding the electron. So in this case, at that distance, about 2 over Bohr radii would be a distance at which you have a node, a radial node, a place where there's 0 probability. So for the 3s, you'd have 2 of them because it goes below and then it comes back up. So twice it goes through 0. So at each of those points, if you squared this to get the probability distribution, you'd see that at those 2 locations, you have a radial node. So there are 2 radial nodes for the 3s. Over here, you're seeing that the 2p has 0 radial nodes, the 3p has 1, and the 3d has 0. Huh, that's interesting. Okay, so p and d orbitals. So for p, L equals 1, for d, L equals 2. The 2pz orbital, the locations of the nodes, this is just looking at the equation. So if we want to know where the nodes are, if we look at the function itself, we know that psi is going to equal 0 at r equals 0, but that's not a node because it didn't pass through 0. They can't go to the other side of r equals 0. But we do know we have a nodal plane, which is different than a radial node. So you have a plane where there's 0 probability at the point at which cosine equals 0. So if cosine equals 0 at that angle, then you have a nodal plane. And so psi is going to equal 0 at cosine theta equals 0, and that's at 90 degrees. So at that point, you'll have a nodal plane. So stop and do self-test 8A.7. And let's look at these two figures. Okay, so this is just reminding you of the shapes. We know the p orbitals have boundary surfaces that look like dumbbells. You have these nodal planes. So we looked at the PZ and saw that at the angle 90 with the z-axis for theta, you have a nodal plane. So a 0 probability, that kind of turquoise plane. The other two, PY and PZ, would have nodal planes perpendicular to that. And then these are the d orbitals. You could also look at where their nodal planes are. They have 4 dumbbells, basically, or 4 lobes for 2 different dumbbells. Okay, so now we're going to think about many electron atoms. So remember, that's anything helium or bigger. So in that case, when we look at it, for hydrogenic, we had 1 electron, 1 nucleus, and so the potential energy simply depended on the distance between those two. But if you have a many electron, even something as simple as helium, you're going to have a +2 nucleus. You're going to have 2 electrons. You're going to have a potential energy term for this electron interacting with the nucleus, this electron interacting with the nucleus. So I'll call those R1 and R2. And then you're also going to have another term for those electrons interacting with each other. And so your potential energy term is going to go from 1 simple term to 3 terms. So the interaction of each of those electrons with the nucleus gives negative potential energy. But an electron both being negative, when you multiply those two, you get a positive repulsion term. And so it's this term that makes it so you cannot solve Schrödinger's equation. You essentially can't separate these variables. You can't separate this guy's location from this guy's location. And so just that simple term right here, the last term in the potential energy, makes it so we can't solve it exactly. And so we have to start figuring out, how do we do it approximately? How do we get as much information as we can? And in 367, if you take that class, you'll learn a lot more about the approximations that are possible. Right here, we'll learn about a simple one. It's called the orbital approximation. So basically what it says is this last term isn't so important, which is stupid because it's very important. But as first approximation, we're going to say the repulsion of electrons isn't that important. And so we're going to use the hydrogen orbitals with different z values for the approximation. So we're going to say that here on the left-hand side, a wave function that's a function of the locations and coordinates of all the electrons can be set equal to a wave function for each of the electrons and then multiply each of those together. So maybe electron number 1 is in an s orbital, electron number 2 is in a p orbital. And so you'd multiply those wave functions together to get the first approximation. You wouldn't just take hydrogen orbitals directly. You'd make sure that you replaced any place where z comes in with the proper z for whatever it is. So if you're talking about a helium, if it's a helium in an excited state, maybe 1 electron in a 1s and 1 in a 2s, each of them will have a z of 2 instead of a z of 1. So stop and do self-test 8B.1, which asks you to create one of these orbitals, which are a function of individual wave function. So it's important to realize that the whole idea of drawing electron configurations, so saying, for example, that lithium is a 1s1 or 1s2, 2s1, that's really using the orbital approximation. So that's an approximation. It's not those orbitals really don't exist in anything except hydrogen. So what is each orbital full with? I'm not sure what I meant there. Oh, I think I meant to say, why is each orbital full with 2 electrons? And that's because of another property which doesn't come directly out of Schrodinger's equation. It comes from relativistic quantum mechanics, and it's the concept of spin. So you learned about this before. A spin quantum number S has a value of plus 1/2 for all electrons. They're spin 1/2 particles. And the spin magnetic quantum number can be plus 1/2 or minus 1/2. We call that M sub S. And that's because the spin could be creating a magnetic moment in one direction or in an opposite direction. And so we call electrons with a spin of plus 1/2 alpha electrons, negative 1/2 beta electrons. Sometimes you say that they're up spin or down spin. And so the experimental evidence for spin, can't believe it's, well, maybe it is figure 2. Let me see. This is just showing you spin is kind of like the particles are rotating and therefore creating a magnetic field. That's not really considered the exact way to think about it, but we do know that charged particles moving create magnetic fields. And so it's an analogous situation. How could you ever figure out if that's true? So when you think about it, this experiment allows you to see that. So if you use silver, silver has 1 unpaired electron. So every time you pair an electron, 1 electron spin up, 1 electron spin down. We're going to see that's as many as will fit in an orbital. Then their magnetic moments cancel each other. You have a magnetic moment in this direction and in the opposite direction. So that 1 unpaired electron in silver, if you pass it through a magnet, on the other side, what you see is that part of the particles were deflected up and part down. And so that means they interacted differently with that magnetic field. This is what it would look like if it was classical, B. But A is what the experiments actually showed, that you could split those silver atoms into 2 groups. One where that unpaired electron is spinning in one direction and one where it's spinning in the opposite direction. So there's experimental evidence for this property of spin, which comes out of relativistic quantum mechanics. Okay, go back here. So stop and do self-test 8B.2. And so out of this idea of spin, the Pauli principle, it says that no more than 2 electrons can occupy any given orbital. So why is it that each orbital is full with 2 electrons? And it's because of the Pauli principle and spin. So, and if you do have 2 in the same orbital, their spins have to be paired. So one has to be up, one has to be down. Same thing as saying one has to be alpha, one has to be beta, or one has to be plus 1/2, one has to be minus 1/2. So before we move into talking about the periodic trends, we're going to think about 2 ideas which are super important. So penetrating and shielding. So how much does the electron that you're talking about penetrate into other electrons and therefore see the nucleus more clearly? Or how much is it shielded? How much do the other electrons keep it from penetrating so that it doesn't see the full charge on the nucleus? So the nuclear charge goes from ZE, so that's the charge. So let's say for helium, Z would be 2, E is just the fundamental charge on a proton, and it goes to an effective ZE. And Gen Chem, you would have just seen it as ZEF. So the effective nuclear charge. So you can think of it, it's not perfect, but if you have 2 electrons, if you have 2 electrons in a sphere around a cation that has a charge of +3, then the nuclear charge is +3. But if you look at it, adding a third electron, that third electron, when it looks towards the nucleus, sees those two other electrons. And so essentially its effective nuclear charge has become 1 because 2 of the protons were shielded by 2 electrons. That's not perfect. You'd have a slightly different number, but that's the idea. So when we're talking about being in the same shell, S's shield less than P's, shield less than D's, shield less than F's. So as we think about building up electron configurations using the Aufbau principle, the order of occupation of the orbitals is given here. And it's really kind of silly to even look at that because you can just look at your periodic table and go across and decide how they fill. And then we must use Pauli's exclusion principle to make sure that each of those only has 2 electrons. So stop and work self-test 8B.3. The other rule we need to know about in order to fill up our electron configuration, so this is all going to be information we need when we talk about periodic trends, is Hund's rule. So if we have Hund's rule just says, Hund's rule just says, I'll find it written so you have it written, but basically just says that electrons like to go into orbitals that are empty before you start pairing them up. Yeah, so on page 372 of the 7th edition, Hund's rule says, in its ground state, an atom adopts a configuration with the greatest number of unpaired electrons. So that would mean, for example, if you have the D subshell and you need to put 4 electrons into it, for example, you'd put 1 individual electron into each orbital first before you paired any, and you'd make sure that they were all either plus or all minus spins. So that's what Hund's rule tells you to do as you're using the Aufbau principle to do an electron configuration. So when we talk about the d orbitals, 3d falls, so 3d falls below the 4s and the 4p in energy by gallium. So 4s and 4p are considered valence. Okay, so once you fill up the whole d subshell, it falls in energy each time you put an electron in. And therefore, by the time you get to gallium, you're going to then put electrons into the 4s and the 4p. And those are then considered the valence. The 3d have fallen so far down that they're considered part of the inner shell. So for cations and anions, that just makes sense. You're going to add 1 extra, take 1 away. You're going to remember the idea about the S's and the D's having different energy as you're taking them away. So you're going to stop and do self-test 8A or 8B.4. Yeah, that'll help you think about reminding yourself that you put in, for example, the 4s, and then you start to fill the 3d. But if you're making a cation, the S's are higher in energy by the time you start taking them out. And so you take the S's out first. So when you do self-test 8B.4, you'll be reminded of that. We'll talk about this last little idea, self-consistent field orbitals. We'll discuss that in class. It's a way to start making a more quantitative correction to the orbital approximation. So rather than just saying you can write the wave function as a product of each electron having its own wave function and ignoring all those interactions between electrons, there's a way that all the big software packages make corrections to that to get better energies for orbitals in non-hydrogenic atoms. So we are done with 8B, and then we'll come back and do another lecture on 8C. I feel like this one was kind of a long one.